Hi there to those of you watching the recording. We're going to start back up today with section 9.3 and then talk about the laboratory assignment. So section 9.3 is all about the addition rule for disjoint sets. And so let's talk about the actual rule. So suppose a finite set has some mutually distinct subsets. Suppose the finite set A has k mutually distinct subsets, or sorry, mutually disjoint. And those disjoint subsets will be A1, A2, etc., up to AN, or up to AK. All right. So what is this thing here? We have k mutually disjoint subsets. N is the number of elements. Nice. So I think that's what they were saying back in our sections from last week, right? They were talking about N being the size of a set. Is that right? So let's see, where did they say that? Yeah, right at the beginning of section 9.1 says there's a notation that N of some set A is the number of elements inside of A. So if we wanted to say this a little bit differently, we could say the size of A is the sum from I equals 1 to K of the sizes of A sub I. Says the same thing, right? Is everybody good with this notation? We went over some notation last term in my class, but maybe I'll ask if anyone else is wondering about that. Okay, so in that case, let's do an example, right? So, so what's an example of, this set A that has k mutually disjoint subsets, right? So what if we had computer passwords, right? So consider passwords that are alphanumeric. Okay, so these passwords would be all of the contents of our set A, right? And then each of these A sub I, well, what could those be? How could you, divide up these passwords into some groups that are mutually disjoint? What would be a way of sort of saying, oh, well, we have this group here, which is separate than this group here, and so on? Any idea? An equivalence relation? Kind of. You could think of it that way, but I don't think that's good. That thought's not going to get you to the answer. But I think that we could think of it as an equivalence relation, though, despite that. So you're on the right track. So we could split them up by the first letter or character, but I think even easier than that, right? So rather than the first one, how about just how many there are in there in general, right? So what if we had, these a sub I would be the length of the password, right? So let a sub I contain passwords only of length I, right? So in that case, we would have, okay, so we'll have, all of the length 1 passwords, all of the length 2 passwords, so forth, all the way up to all of the length k passwords for however, whatever our maximum password length is, right? And does it make sense that, if these were all distinct, then we can add up their sizes and get the whole set? Well, what if we split them up by first letter or the first character, as Sean said? Would that work as well? Yeah, I think that would work too, right? So, if we had all the passwords that start with A, all the passwords that start with B, etc., right? That would make those subsets disjoint, which really is the main thrust of what we're getting at here. These have got to be separate, right? And so as long as it's disjoint, it's always going to work. Yep, that's exactly right, Sean. Good. This is just the example that your book used, but your example works fine too. Yeah. Okay. Um, so let's do a little computation then, right? We'll stick with the book's example for a moment in order to do this computation, because I think that's where this example is going to be a little bit easier to compute, right? Um, so if we wanted to compute, these are alphanumeric, so there's going to be 36 different characters, right? 26 letters and 10 digits, right? So how many different passwords can we make for a sub 1, right? So in other words, what's the size of a sub 1? 36. Good. How about a sub 2? Yep, 36 squared, right? As long as there's no restrictions about, repeating characters or anything like that, right? As long as we're free to choose whatever we want. And you're absolutely right then. A sub I, the size of a sub I, is equal to 36 to the ith power. Nice. And so if we wanted to know the size of A, right, what would that be? So if there we go. Okay, so we have the sum from I equals 1 to the max length. So we'll just call that K for now. Of 36 to the I, not factorial, just 36 to the I, right? Yeah. So let's see. So do we want a factorial on there? We don't. Okay, you take it back. Okay. Yeah, because if we think about those slots again, like we were saying last time, right? So we've got you know these characters here. Character number 1, 2, 3, up to K, right? And since we can do 36 at each location, right, we would just multiply all those together for a K length password without that factorial. Yeah, good. Okay, so let's do another example, right? Um, yes, that one is easy to look up actually. Yeah, so if you want to actually evaluate this guy, right? So yeah, you would look up how to simplify this sum, which I think we could do, right? So that's some good practice. How would we figure out what this sum evaluates to in the closed form? Any ideas? All right, so it's equal to 1 minus r to the n plus 1 divided by 1 minus r, where r is 36 and n is k. Okay, so this would be 1 minus 36 to the k plus 1 divided by 1 minus r. So that, I guess that would be negative 35, right? So the whole thing would be 36 to the k plus 1 minus 1 divided by 35. But that's for some that starts off at I equals 0. Well, I think we could even maybe include that, right? Because how many passwords of length 0 are there? Right, so if we included passwords of 0, like this, and we added on, you know, we added that on. So what would be a sub 0? Would it be 36 to the 0th power? Yeah, that would add 1, right? That's saying that there's one password of length 0, which is, you know, maybe the empty password, just like not having a password, right? Um, yeah, so there's this question: is it real, right? Does it count, right? And that all depends, right? Maybe on your computer, you are allowed to just log in without putting in a password, or maybe you're not, right? So I think that all depends. I think there's either 0 or one of these, depending upon the rules of the password generation, right? And so I think you could either leave that leave that extra one included here, or or get rid of it, which would be up to you, right? Okay, cool. So let's do another example here. All right, so let's count up how many 3-digit integers are divisible by 5. Okay, so what do you think? Okay, 999 divided by 5. Well, that's not going to be a whole number though, right? David, you're saying 180? Okay, how'd you get that? So Nathan, you're on the right track there with your idea. It's just a little bit off. Okay, 20 numbers from 0 through 99 and 9 increments of that. 8, which gives you 160. Okay, so do we want 160 or 180? $160. No 180. Because we want 9 increments of that, not 8 increments of that, right? Because we're going to have the increments 100 through 199, or yeah, 100 through 199, 200 through 299, etc. And how many of those will there be? Well, there'll be the 100s, 200s, 3, 4, 5, 6, 7, 8, 9, right? So there'll be 9 groups of those numbers, right? And there's 20 in each increment. Okay, so that makes sense. 180. What's a way that we could divide up this this set of integers divisible by 5 into 2 mutually disjoint subsets, which may be easier to count? Any ideas? Yeah, and in 0 or 5, right? There's 2 groups of numbers divisible by 5. Those that end in 0, those that end in 5. What do we know? What further do we know besides that those sets are mutually disjoint? So we know something else about those 2 sets besides just that they're disjoint. Maybe we should walk through the problem. So let's just count how many ended in 0, right? So how many increase by increments of 10? Yeah, that's true. So we can sort of think of it that way, right? So how many for for the numbers from 100 through 199, how many numbers are divisible by 10? Or how many end in 0, right? Not 9. Close. 10. There we go. Right? And what do we know about how many end in 5? Yeah, also 10, right? It's going to be equal, right? So that's what we know about those numbers that end in 0 or the ones that end in 5. In each of these groups that we're looking at here, we're going to have an equal number of examples that end in 0 and those that end in 5. And so in that way, we can say, okay, well, obviously there's 10 of these, right? Because we got, 100, 110, 120, and so forth. So there's 10 of those. We have the same amount of those that end in 5. So total, we have 20 in 9 regions. So 20 in 9, I guess I'll say ranges, right? Gives us 180. Right? So, dividing it up into these 2 different subsets might, maybe that would make it easier for you to think about how to count them. Possibly. Maybe not. That's up to you. Right? Okay. Any questions about that one? All right, so let's talk about the difference rule, right? If we're talking about the size of the set A minus B, assuming that B is a subset of A, right? Right? What's this going to be equal to, do you think? So if we have two sets, A and B is contained in A, right? So we have, sort of this situation, right? Yeah, and we want to know the size of A minus B. Well, that would be the size of A minus the size of B. Well, why is it important that B be contained in A? What if B was not contained in A? Would this still work? Yeah, if there were elements of B that were outside of A, that were not in A, those wouldn't get subtracted out, right? If we had, sort of this situation for B instead, right, then all of the elements over here would be, subtracted off from A, right, when we did this. But it wouldn't really make sense to subtract them off, because you're not taking them away from the number of elements inside of A in the first place, right? So so maybe we should do a little example here, right? And we can sort of think about it both ways. All right. So let's think about these some more of these passwords, right? Um, so consider um, 4-character alphanumeric pins. By pins, I just mean passcodes, right? Like a pin for your ATM card, right? Now, if we have 4-character alphanumeric pins, right, and we're wondering, how many with repetitions allowed, so you can repeat stuff, right? Let's ask about how many of them are repeated, right? How many pins have repeated characters? Okay, so Sean in the chat, you were saying, if we didn't have B contained in A, we would only be able the size of A minus B be the size of A minus the size of the intersection of A and B. Yeah, I think that's exactly right. It just so happens that the intersection of A and B equals B when it's contained inside of A, but otherwise we would only want to subtract off the intersection, which would be, that part, right? This is the intersection part here between A and B. So that's what we would subtract off to get the size of, A minus B, right? Okay, so that makes sense. But let's see if we can use that idea to answer this question, right? How many pins have repeated characters? So what do you guys think? Okay, calculate the total number of pins. Okay, so total pins is how much? Okay, then subtract off the not repeated pins. Very nice, right? And oftentimes that's going to be an easier thing to calculate than the ones that do have repeated characters. So look, we're going to sort of look at this both ways, right? So first of all, what's the total number of pins? Oh, and David, you guessed 36 to the third, almost 4 character pins. So it'd be 36 to the fourth, right? Nice. Okay. How about the ones with repetition? Oh, sorry. Without. I'm sorry. Wait. Did I do that wrong? Yeah, sorry. Without repetition. Without repetition. There we go. 36 times 35, 34, 33, right? Because you can't use any of those repeated items in each further slot for slots 1, 2, 3, and 4, right? So if you want the ones with repetition, you can just subtract those, right? So with repetition equals 36 to the fourth minus 36 factorial divided by 32 factorial. Okay. What if we didn't do it this way, right? What if instead we said, okay, well, we're going to try to find the ones that have repeated characters. Okay. Well, let's try to do our slots style, the solution to this problem, right? So we have these 4 slots. Maybe I'll just come up here. So we have 4 slots, and we want to put things in the slots, but we have to have something be repeated, right? So how would we do that? Okay, one slot has a 1, the rest have 36. So, okay, so why would one slot have a 1? What's going on there? One slot has a 3 because there are 3 characters that could repeat. Ah, okay. So, and David, you said choose any number, 36 choices. You have to match the number, only one match. 36 possibilities for the other 2. Yeah, but it can match any of the 3 options. Okay. So I do kind of like that idea where we have 36, 36, 36, 3, right? I think that makes sense, right? But there's a little bit of a problem with that, right? Because if you were wondering about who gets, how many different repeated ones there are, there's a bit more complexity. Yeah, we need to divide it into cases, right? Did it repeat 2 characters? So one thing gets repeated. So there's a total of 2 that are repeated, right? Or are there 3 repeated, or are there 4 repeated, right? So we can say, is it 1 rep, 2 rep, or 3 reps, right? So maybe we should call those are going to be disjoint, right? So maybe we could call those, A1, A2, and A3, right? where this is the number of repetitions there are. So if there's one repetition, or let's say that there's 3 repetitions, right? So we have, you know, in that case, let's go. I think that might be the easiest one to start with, actually. So how do we compute this? Maybe I should label. I like Nathan's labeling better. I'm going to call this A4, this one A3, and this one A2. Right. So here there's all 4 things are repeated. So what do we get to choose? Yeah, 36 ways, right? Because we can pick the first one, 36, right? But then all the rest of them, we don't have any more choices, right? Because those all have to be the same as the first one because they're all the same. Yeah. So the total number of ways would be 36. Okay, how about A3? What's going on here? Well, you're getting there. So that's part of the answer. I mean, you might think that I could do 36 here, 36 here, and then, but this one's a 35, right? So there's a 36, a 35, because this one's not repeated. And then we also have this one. You could choose to repeat either this one or this one, right? So this one would be a 2. And this one, you have to do the same one that you repeated here. So that would be a 1. Okay, does that make sense? So you pick whatever you want here. This one has got to be different than that one. And this one's going to be the same as this one, and this one's going to be the same as this one, right? But that's not all. Right? So let's do an example of A3. So we could have, you know, let's say R, you know, Q, and then R, R. Yeah, we also need to account for the positional switch, right? So that's kind of interesting, right? We have RQRR, but could we have the password QRRR here? We could. Okay, what about this one? RRRQ. Could this password be generated from this scheme? It should be able to be, but is it? No. Good, why not? Yeah, it has to be the same as the second to last one, right? So that's interesting, right? So this is getting pretty complicated, right? So what's a good way of counting these, would you say? Yeah, how many ways are there to arrange 2 characters in 4 slots where 3 are the same? Okay, so Sean, you have it all there, but let me sort of rearrange the order of your ideas a little bit. You're going to be picking 2 letters, 2 characters, I should say, right? You're going to pick a Q and you're going to pick an R, right? You're going to pick two different things. One of them is going to be the repeated one. The other one is not, right? So in order to pick those guys, it has to be two different ones, because if they were the same, we would come out with all four of them the same, and we've already accounted for those, right? So they do have to be different. So we'll have, 36 times 35 to start off with. And then the other thing that we're choosing, right, is what? Besides which R and which Q, what's the other thing that we're choosing? Yeah, the location of Q. So times 4. That's exactly right. Right? Is Q at the first, second, third, which I didn't do, or fourth slot? Right? So we choose which slot the one that doesn't belong is in, slot 1, 2, 3, or 4. Right? So we pick our two different characters, and then which slot has the different one. So this would actually be times 1 times 1, right? Times the different positions of the different one, right? Which is not, there's not really a good way to, we can do a little arrow or something, right? We could say, oh, we're gonna, switch these guys. Or, there's not really a good way to say it. So we'll just say times 4, right? So 36 times 35 times 4. Okay. Well, what about A2? What's going to happen there? Well, again, I don't think thinking which one to duplicate is necessarily the best way of going about this. I think that might make it a little bit more complicated than it needs to be. So let's try to think about it in terms of what we did here, right? So we figured out how many different characters we needed, right? And then we thought about the positions. So if we have only one thing being repeated, well, no, I guess in this case we have, well, it's even worse than I thought. I forgot about a situation. What else could happen besides one thing being repeated? So we could have, P, Q, R, Q, where, Q is repeated. We could also have two pairs, right? So we could have A2 and then also A22. Well, well, how are we going to catch? Should we count those as separate? Right, because we could also have, P, Q, Q, P. Do we need to count those as separate things, one pair versus two pair? Can we just combine them all into one thing? What do you guys think? Well, let me give you a little hint, right? What if I went about it this way? What if I said, okay, well, I'm going to pick 3 different characters, okay? So P, Q, and R, and then, the position of the repeated one, the position of this guy, right? Well, if I did it that way, that would exclude all of the 2 pair ones, right? Because I pick 3 different things, how could I have 2 pairs, right? So if I counted it that way, it would exclude 2 pairs. I don't have to count it that way, but but I could, or maybe I could say, well, I'm going to just count P's and Q's, and then whatever else is down, whatever other junk is down here, well, then there you go. That's fine, right? But I think that way of counting could be problematic, right? I just pick, I just pick P and Q, and then these ones I just leave blank to be whatever you want. What could go wrong with that? Why couldn't I count it that way? No matches. I'm not sure what you mean by that, David. PQRS. Oh yeah, I could have no matches in there. Yep, that's true. Absolutely. I could also have triples in there. I could also have PQQQ. That's the one I was thinking of, but we're both right. Right? There's two different ways that that could go wrong. Yeah, we could have PQRS, that doesn't have any match. We could have PQQQ, that falls into the triples category. So I think that's a really bad way of counting, right? P and then Q and then whatever you want, right? So we need at least one P or one Q, right? So I think counting this way would be easier, right? Saying we have P, Q, and R, and then a repeated thing, which can go in, any of four slots, right? So we have P, Q, and R. We have a repeated one. So do we want that times 3 in there? Does it matter which one gets repeated? So is Nathan right by saying we should have 36 cubed times 3, or should we just have 36 cubed times 1? Ah, okay. So first of all, we need to be decreasing. So we need 36, 35, 34, because these all need to be different, right? So if we have, well, I'm concerned, Nathan, that with that times 3 on the end, we may be double counting things, right? So if we have P, Q, R, and then Q is which one we're repeating, right? Well, I'd be concerned that that maybe if we just hmm, would we be double counting if we multiplied by 3? Do you think? So what do you guys think here? Okay, it seems like you guys are a little lost. So let me help, right? So if we're going to include a distinction for the location of which item is the repeated one, right? Then I think we could run into the problem where if we say, okay, well, if this one is the repeated one here, and we count that, and then we separately count when this one is the repeated one, then we would be double counting, right? So I think maybe a little bit better way to think about it is we pick three different characters, right? Then we pick the location of the repeated one. Pick the location of the single repetition, right? And then if we do that, do we still have to include that times 3 on there? Do we still have to include which of the 3 characters we repeated? Maybe. What do you guys think? No. Okay, why not? So let's pretend that we do need to. Okay, we'll say okay. So we'll pick which character is repeated. Okay, and let's say these are our rules to generate um, pins with one pair in them somewhere, anywhere, right? Any pin with one pair in it. Okay, and let's see if we can use this to generate a double counting, right? So we're going to pick three different characters. Okay, so I pick P, Q, and R. Okay, those are my three characters. I'm going to pick the location of the repetition. Okay, so let's say, I pick that the first slot is going to be repeated, right? So here, I'll pop over here. So let's say, here's my rep, and then I have, P, Q, and R are here. Then I pick which character is repeated. So I could have P or Q or R in here, right? Okay. And let's
Oh,
say, oh, go ahead.
I
Yeah.
was just going to say, it just occurred to me why there would be double counting.
Okay. Why is that?
Because so you pick the three different characters,
Mm-hmm.
and now you have a fourth character, and it's a repeated version of one of them.
Yep.
When you pick which place the repeated character goes in, you're going to double count because no matter which character you pick to be repeated, you're going to count the version where that's the repeated character and the version where that's the original character twice.
There it is.
Does that make
Yep.
sense?
Yes, perfect. That's a
Okay.
great way of putting it. Yep, very good. So you could think that the original P is here and there's a repeated P here, or you could think that the original P is here and the repeated P is here, but you're counting the same thing twice. That's perfect. That's exactly right. Right. So I think if we don't pick which character is repeated, let's say that we don't do that. Does this work then? Is this correct? We pick three different characters and pick the location of the repetition. Then are we counting everything? And are we counting everything exactly once and not double counting? Or did we miss something? Or did we still double count? Sean, you think that gets it all? So let's see. So can we build anything we want, right? So so let's see if we can build this PPQR situation, right? PPQR. Can we build that? Okay, so we're going to pick three different characters, P, Q, and R. Okay. And then we pick the location of the repetition, which I guess would be, I don't know, let's say the repetition is going in this first slot again, right? Well, how do we do QPQR in that case? So you don't see it? Okay, so that's all right. So maybe we should go back to the other way. So if we do include which character is repeated, right? We do know exactly how much we're double counting. So that's kind of nice. How much are we double counting if we know, if we're picking which character is repeated and the location of the repetition, how much are we double counting by? Yeah, we're counting twice, right? So what we could do is just divide the whole answer by 2. Yeah, exactly, right? So we could say, okay, we pick 3 different characters, right? So that would be 36 times 35 times 34. Okay. We pick the location of the repetition, which is 4 different locations. Pick which character is repeated. Well, that would be times 3. And then we divide that whole thing by 2, right? Let me just consider this little chunk of the situation for a minute here, right? Another way to think about this, instead of picking where the location of a repetition is 1 slot, right? The location of a repetition really is 2 spots, right? It's the, here's one of them, here's the other one. It's both locations of the repeated items, right? So in that case, what we're saying is, okay, well, we're going to pick the 2 different locations where something's repeated. Well, if I want to do that, right, the 2 different locations where something's repeated, well, what are my options? Well, I could do these ones. There's 1, right? I could do these ones. That's 2. I could do these ones. That's 3. And I could do these ones. That's 4. These ones is 5. And these ones is 6. Sorry, that kind of went all over the place. 4 choose 2, right? So maybe I should write it a little better. I can do 1 2, 1 3, and 1 4, right? So there's 1 2, 1 3, 1 4. I could do 2 2, 2 3, and 3 4. 4 choose 2 is 6 total. So you could think about this as 4 different locations times which one you're repeating divided by 2 for double counting. Or you could have thought of this just as times 6, right? 4 choose 2. So it does work either way, but again, it's pretty complicated to figure out, right? Okay, now we're almost there, right? Because we have A2, A3, A4, but I'm also worried about when we have 2 pairs, and I'll call that A22, right? Right? So again, let's go through our little list of what we're picking, right? How many different characters are we going to pick if we have 2 pairs? So now we want 2 pairs. So how many different characters do we choose? 2, right? 2 different ones. So it'll be 36 times 35. And what do we have left to choose? 2 2 1. I'm not sure what you mean there, David. So how about just in English? Like, we have to know what the 2 characters will actually be. Okay, so that's what's covered here, right? We pick, out of the numbers and letters, we pick, the letter R, and here we pick the number 4, or whatever other character we feel like, right? So these are picking the 2 characters. But what's the other thing we need to be worried about just besides the identity of the characters? Yeah, the positions of the characters, right? And now we're working with 2 pairs, right? Yeah, the location. Yeah, exactly. And so again, there's 6 ways to arrange them. Is that right? So if we have, let's think about this. So we could have, is it the same as these guys here, these 6? So we have a pair in 1, 2. Yeah, I think you can still use these to think about it, right? So you could still have 1 pair in 1, 2, the other pair in 3, 4, right? Or you could have a pair in 1, 3, the other pair in 2, 4, right? or you could have a pair in 1, 4, the other one in 2, 3, right? So, okay, so then I have 2, 2. Oops, I should have said 2, 3, and 2, 4. Sorry, I screwed that up. 2, 3, and 2, 4. That's better. Can't be at the same spot. Okay, so we could also have 2, 3 be the pair and 1, 4 be the other pair. Uh-oh, what went wrong? I've double counted again. Can you see where?
So is it because 2, 3, and 1, 4 are going to be the same thing? It just depends on which one we pick to be the inner ones and which one we pick to be the outer ones?
Yep,
We've already
exactly.
accounted for that by multiplying 36 by 35.
Exactly right.
Okay.
Yep. And same thing with 1, 2, and 3, 4, right? These are the same. So you're double counting those. And 1, 3 versus 2, 4, those are the same. So you're double counting those. Right? So we actually just want to multiply by 3 because there's only 3 different positional ways to arrange those guys. Cool. So, moment of truth, okay? We did our original idea, which is to count all the pins without repetition and subtract it off. Then, instead, we did another method where we calculated the ones that actually do have repetition, right? And we divided it up into these 4 disjoint subsets, computed each one. Let's add all these up and see if it's equal to the same answer that we got over here, because by golly, it should be. I hope so, unless we screwed something up, right? So, so let's make some little notes here. So we've got our original computation is going to be 36 to the 4th minus 36 factorial over 32 factorial. And let's see how much that is. So let me pop over to my calculator here. All right, 265, 896. All right, great. Okay, so now let's look at all of our other ways that we did it. So let's look at A22. We'll do that one first. That's 36 times 35 times 3. Okay, 3,780. Okay, so A2, that's 36, 35, 34 times 6. Okay, 257, 040. Okay, how about A3? Well, that's going to be 36 times 35 times 4. It's going to be 5040. And lastly, A4, of course, equals 36. Right? Okay, so let's add all these guys up and see what we get. So that'd be plus 36 plus 3780 plus 257.40. Grand total, as expected. Thank goodness that worked. 265, 896. Exactly the same as what we got up here. Nice. Right? So what's the moral of this story? I'll let you guys tell me the moral after that that little nightmare that we had, right? Good practice. A little bit nightmarish practice though, right? So what's the moral of the story? Okay, that's one moral. Counting is hard. Good point. What else? Yeah, do the first method, right? There are multiple ways to count things, and some ways are easier than others, right? And you know, so picking which method you're going to use is really, I think, the most important part of counting, right? Because it's, you know, if you pick the wrong way, the chances that you're going to make a mistake when you're counting all this stuff up is pretty high. That's pretty hard to do, right? So if there's an easier way of doing it like this, well, heck yeah, pick the easy one, right? Okay. Is everybody happy with that? Any questions? All right. So, um, so let's do this. Why don't we take a short break? I know that was intense, right? So why don't we take a let's take a 5-minute break, stretch your legs, stretch your brain, get the blood flowing, and we'll come back in 5. See you soon. All right. So the next rule that I want to tell you about is called the inclusion-exclusion rule. Okay. Which is to say that the size of A union B is going to be equal to the size of A plus the size of B minus what? Good. The size of their intersection is what we subtract off. Good. Right? Because if we add together A and B, then we've double counted the intersection, right? So if we're thinking about it, you know, this way, where here's A, here's B, right? Well, if we're adding A plus B, we've added this area in twice. We added it in once for A and once for B. So we subtract off one of them, and that's how we get the entire union, like this, right? What do you guys think? Does that make sense? Makes sense. Okay. So let's do an example. Let's say, you know, so we'll do a real union here. Let's say, how many 3-digit numbers are multiples of 5 or 3? Notice I said or. That's why we're doing a union here, right? Set A will be the numbers that are multiples of 5. Set B will be the numbers that are multiples of 3. And there will be some overlap between those. What will be in the overlap? Yeah, numbers divisible by both, right? In other words, numbers divisible by 15, right? Those numbers will be divisible by 5 and 3, and those will be in the intersection. We don't want to count those twice, right? So what's going to be sort of my strategy here? Okay, so okay, so there we go. How many divisible by 5, add how many divisible by 3, and subtract divisible by 15. Yeah, perfect, right? Because if here, this is my div 5, and this is my div 3, and in here is my div 15, right? Divisible by both, right? Then I'll have my idea is going to be the size of div 5 plus the size of those divisible by 3 minus the size of, how many divisible by 15, right? Okay. So, well, Nathan, do we want that plus 1 on there? Yeah, I suppose we do, right? So we'll have 900 divided by 5, which is, as we saw before, 180, right? How many 3-digit numbers will be divisible by 3? 300. Okay, okay, same logic, right? 999 minus 100 plus 1 divided by 3. 900 divided by 3 is 300, okay? And how many divisible by 15? I guess that would be 900 divided by 15. So how much is that? $60, okay? So we have 180 plus 300 minus 60, so 120 plus 300, 420, which it was yesterday, right? So, okay, so it looks like we have 420 as our answer. 420 numbers that are divisible by 5 or 3, almost half, right? Okay. Any questions on that? Ooh, but I'm seeing a different answer here in the book. Oh, I see. That's from 1 through 1,000. Yep, the book included 1 and 2 digit numbers as well. So that's a different answer. Okay, cool. We just did a different problem. That's fine. Just making it didn't match, but that's because we did a different question. In the book, instead of having 3-digit numbers, had 1, 2, or 3-digit numbers. Similar sort of idea. Cool. Okay. So moving right along. If we were to have 3 sets and wanted to write down the inclusion-exclusion rule, what would it look like? So I'll get you started. Size of A plus the size of B plus the size of C. And then what happens? Okay, then we subtract off all of the intersections, but now there's 3 different ones, right? So now we're subtracting off A intersect B, and A intersect C, and B intersect C. But what do we do with the intersection of all 3 of them? We add it back in. Great, why? How did that happen? If you think about, let's make a little picture here. We did subtract it out 3 times, but that doesn't mean that we add it back in twice. So let's think really carefully, right? So if we're adding up A, B, and C, right, then these guys here get double counted, right? The overlaps. This guy in the middle gets triple counted. So it gets counted once for A, once for B, and once for C, right? But when we subtract these guys off, it gets triple subtracted, right? So here it gets triple added, here it gets triple subtracted. So at the end of the day, this center region in here is not included at all. So we add it back in one time. Yeah? What do you guys think? People happy with that? Great. Awesome. Okay. So let's do a bit more practice, huh? Lots of problems to practice with at the end of 9.3. Okay, and actually, why don't I bring up, let me bring the proofs up real quick here because I forget which ones are proofs and I don't want to do them for you. So, and I'm definitely happy to talk about them as well. So here, why don't I stop sharing and we'll look at the proofs for this week. There we go. All right, so assignments, proof 4, there we go. All right. So here's the graded proof. Consider strings of length n over the set 1, 2, 3, 4. One element in the set of strings of length 5, for example, could be 1, 2, 4, 3, 2, right? So the set is always 1, 2, 3, 4, but the length could vary. So if the length is 5, the things we can pick from are 1, 2, 3, 4. Well, 1, 2, 4, 3, 2 is one example. Okay. What is the probability that a string of length n has at least 2 numbers that are the same next to each other? Like 4, 3, 1, 4, 3, 3, 1. So the 3 and 3 here are next to each other. So what's the probability that you have at least 2 numbers that are next to each other? Could be more. Could be 3 numbers next to each other. Could be 2 pairs of 2 numbers next to each other. Right? Lots of different, 4 numbers next to each other. Lots of options here for at least 2 numbers next to each other. Right? Okay, so that's your graded one. For your collaborative proofs, we're thinking about m different prime numbers that are all positive integers. Oh, and and another sequence of a's that are positive integers. Yes, because we're going to do a divisibility proof. So n is p1 to the a1 times p2 to the a2. So this number is a product of primes, right? A product of exponentiated primes, right? In that case, how many divisors does n have? Prove a formula using the multiplication rule with an induction proof. Okay, there's our first induction proof of the term. So that should be fun. And our second collaborative proof is a gambling proof. Okay, so it's a good idea to have a stopping condition when you gamble. Like if you lose $100, that's a good point to stop, right? So here's this gambler stopping condition. They decide to play until they lose 3 times in a row. That's their stopping condition, right? So let W and L denote wins and losses, and A sub n denote the number of arrangements of wins and losses with n games. And here's all the different possibilities of wins and losses for the verse value of A sub n, right? So losing 3 times in a row, that'll get you to stop. These are all the stopping conditions, right? So for A3, there's only one stopping combination, lose, lose, lose. Okay, for A4, there's only one stopping condition, win, lose, 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 right? You can't have lose, 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 because if you had 4 losses, you wouldn't have ever done the 4th one because you would have stopped. Bless me. You would have stopped after the first 3. So you couldn't have like 4 L's in a row, right? Let me bring my chat window over. Yes, bless me. Thank you. Appreciate it. Okay. You also couldn't have lose, 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 win, because if you had 3 losses at the beginning, you would never play that 4th game that you would win, right? So here's an example where you actually could have 2 different arrangements, right? Where you lose 3 times at the end. So you could have win, win, lose, 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 or you could have lose, win, lose, 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 right? You couldn't have win and then 4 losses because again, you can only at most have 3 in a row. So hopefully you're getting the idea here, right? So here's A4. You have these 4 different possibilities, okay? So bearing in mind that any sequence of n games must start with the arrangement win, win, or loss, win, find a recurrence relation that gives a formula for the number of arrangements of wins of losses, A sub n, right? So we're going to do a couple examples of recurrence relations. So if that idea bothers you, don't worry. We're going to do a couple samples here of that. But the basic idea here is you can use recurrence relations as a sort of as a shortcut here, right? Because if you can find a formula, if you can find a pattern between A5, A6, A7, and so forth in the form of a recurrence relation, well, last term we learned how to solve recurrence relations in their closed form, right? So rather than counting up all the different possible little arrangements that you have here, instead what you do is you say, okay, well, I know a formula to get from, one set of wins and losses to the next one. And if you solve for that formula, that'll give you your total that you want, right? Is everyone happy with that idea? Does that make sense, or do people have questions? Okay. Well, just let me know if you think of any questions here, and we'll do some examples. I should actually that. Okay. All righty. Okay, so let's start out with kind of a cute one. Okay, so a company has 6 new employees that are going to be seated at 6 desks lined up in a row. So, okay, 6 new employees. They're going to occupy 6 desks. Let's label them 1 through 6. Okay. 2 of the employees are married to each other. So these new people that got hired, 2 of them are a married couple. Right? If the assignment to the desk is made randomly, what's the probability that the married couple will not be sitting next to each other? Okay, so what's the probability that the couple is not sitting next to each other? I'll say sitting adjacent. Okay, so what do you guys think? How should we approach this question? Get the total. Okay, good. And then, so I like your underlying strategy that you're using here. So get the total, then what? Yeah, minus, right? Then we'll subtract the ones where they do sit next to each other. So we want the total minus they are sitting next to each other. So I'll say total minus adjacent, right? Total minus adjacent, that'll equal non-adjacent, right? Okay, so let's get the total. So how many total ways could we arrange these people into their desks? Well, how many choices do we have for the first desk? Yep, 6, 5 at the second desk because we already sat one person and so on, multiplying everything together, 6 factorial. Very good. Okay. Now, what are the, how many different arrangements are there where the married couple is sitting next to each other? So how would we count that? 6 choose 5. Okay, so why would that be, Sean?
The couple acts like a single unit.
Okay, sure.
So you're only picking maybe it's 5 choose 5. You still have 6 slots, but it's like having 5 slots and 5 things to pick from.
Okay, so you have the married couple sitting sort of like here and here is one option, right?
Mm-hmm.
Or here and here, or here and here.
Right.
Okay, well that
Because
would
they're next to each other, they act like a single thing.
okay, sure. So we want to pick so to pick adjacent. So let's do a little side note over here. So adjacent, that's going to be the position of the couple. Okay, so we're going to pick the position of the couple, and how many different positions could the couple be in? Like, can they be 1, 4? Could they be 3, 4, 5, 6? Like, how many different ones how many different arrangements would we have there? Yeah, 5 of them, right? Because they could be in 1, 2, 2, 3, 3, 4, 4, 5, or 5, 6. So it'd be 5 of those. Is that all that we're picking? So we just subtract 5 off of this thing? Yeah, we also need to arrange all the other people too. So once we pick where the couple's sitting, we still have the other 4 people to place, right? No matter where we seat them. So if we seat the couple at 1 and 2, we still have 4 people left to pick where they're supposed to go. Or if we put the couple at 5, 6, then we put the other 4 people in 1 through 4. So the arrangement of all those around them, we also want to arrange the other people. That would be 4 factorial, right? So it looks like I have 5 and 4 factorial. How do I combine those things? Do I want to multiply those, add them? Yeah, you multiply them, right? Because for each arrangement of the couple, there's all these different arrangements for the other people. So those are going to be multiplied. So it's 5 factorial. That's right. Okay. Which is going to be 120 minus 24 is 96. Okay. So we're almost there. So we have 96 non-adjacent arrangements. But what I wanted is the probability. Oh, we're doubling it? We could arrange the couple too. Okay, so so maybe we have, one partner A here and partner B here, or we could put them the other way. Okay. So so the position of the couple is 5, other people is 4, and then which partner is where? That'd be another 2. Okay. Yeah, that's fair. So then I guess we would have 120 minus 48, which would give us would that be 72, right? Yeah, 72. Okay. Is that right now? Think so? Okay. So then how would we compute our probability then? So our probability, of course, is equal to the total, or sorry, the number of successes, or the number of actual, I'll say the number of true outcomes divided by the total number of outcomes, right? Which of course in this case will be 72 divided by, oh, I totally did this wrong. Oh boy, that's supposed to be, I'm sorry, I screwed this all up. 6 factorial is 720, right? And 5 factorial is 120. So sorry, one more try here. 720 minus 2 times 120 is going to give me 600, 480. Sorry, I did my wrong factorials. So it'd be 480 divided by 720, which will be how much? 2/3. Well, now that's kind of interesting. That's a really nice round number. So 2/3 probability the couple is not sitting next to each other. So then what's the probability that they are sitting next to each other? Yeah, 1/3, right? Because of course these probabilities are all going to add up to 1, right? Because probability is a percentage, and percentages always add up to 1, right? Okay, so let's think about that for a minute. I mean, can you see why there would be, either way, why there would be a 1/3 chance they are sitting together or a 2/3 chance that they're not? Is there a sort of a simple way of interpreting that nice round number answer? Okay, they're a couple and it only has 6 chairs. So yeah, so maybe there's something to do with the 2 and the 6 versus the 4 and the 6. Interesting. Yeah, so maybe that has something to do with it. I'll let you guys think about that. That's a nice little brain teaser there. I'll leave that for you guys for later. All right, so let's try another one. Let's try one of these recurrence relation ones and see how these things work. Right? So consider the set of strings of A's, B's, and C's. So we have some strings made of A, B, and C. Okay. Okay, so the first part here is list the strings of various lengths that don't contain the pattern AA. So we're going to keep looking for during the problem, strings made of A, B's, and C's that don't contain the string AA. Okay, so let's do a little table here. So here's the length, here's the number of strings. Well, let's just actually do a list of strings. So we'll do the length and we'll do the list of strings of that length. How many strings are there of length 0 that don't contain AA? Yeah, 1. Very good. The string with nothing in it, the empty string, right? Okay, so that one's kind of tricky. This one's a little easier. How many strings of length 1 don't contain AA? Or I'm sorry, so list them out. What are they? Maybe I'll do strings here, and I'll do the number over here. I'll do another column. So here's the string, the empty string. Yeah, we'll have 3 of them, which are A, B, and C. I'll separate my strings with commas here. So 1 of them here, 3 of them here. Okay, how about strings of length 2 that don't contain AA? So let's list them out. In fact, we could list out all of them and then just cross out AA, I guess. More than 5. Yeah, 7. Well, nope, not 7. Almost there. Thought you were right. Okay, so there's 6 of the strings that don't contain AA, but there's more. Yep, 8 total. Very good. So if I was going to list them all out, AA, AB, AC, right? BA, BB, and BC, CA, CB, and CC, and I'm not allowed to have AA in there, right? So I'd have 8 total. Very nice. Okay, so let's try strings of length 3. Now this is going to be a little harder. So if I wanted to list out all the strings, right, and then maybe subtract off the ones that have an AA inside, right? Maybe that would be a clever way of doing it. So how would that work?
Oh, I was thinking you could also take the 2 right-hand columns, AB, AC, BB, BC, CB, CC, multiply that by 3 because you can tack 3 characters on the end of each of those, right? So that's 18. And then for BA and CA, we can tack 2 things on the end of those. So then that's times 2.
Okay, so this we can tack 2 things on the end because we can add on either a B or a C to either one of these. These guys at the end of the string, we can tack on A or B or C, right? Because since we have a B or a C in the second position, if we can add on an A in the third position, and this either B or C in the second position will buffer it, so it's not sitting next to another A. I like that. That's actually exactly where we're going with this, into that recurrence relation that I was talking about. So that was a great lead in there. Okay, so it looks like we'll have 18 plus 4, right? 2 times 2, so 22 total. Is that right? Well, how many would there be total? What if we did include the strings with AA? So let's try to approach it a different way and see if we get the same answer, right? That's always someone was saying earlier, Tamara maybe? Someone was saying earlier it's always nice to be able to check your work, right? So what's the total number of strings we could make, including all the double A's? 27, 3 times 3, right? Because we would have, 3 choices here, 3 choices here, 3 choices here, and we're multiplying these, right? So we get 27 total. Okay, so then the question is, okay, if we're going to do our subtraction method, could we come up with 5 strings that have an AA inside, right? Because then 27 minus 5 would give us our 22 that we're looking at here, right? So can we come up with 5 strings that have AA inside? And there they are, right? AAA, AAB, AAC, then BAA, and CAA. Perfect. Okay. So here, why don't I put in here not, and I'll just list out the ones that it's not, because I don't want to have to list out 22 things. AAA, AAB, AAC, BAA, and CAA. Right? Okay, cool. So I did like that that idea with the with this recurrence relation, the times 3 and times 2. So, so how does that work, right? How am I going to, find a formula for this guy that uses that sort of uses this breakdown, right? Any ideas there?
So how many from the previous number end in A? Multiply that by 2, and how many from the previous number do not end in A? Multiply that by 3, add them together, and that should work every time.
Okay, so here's our idea: 2 times end in A, and 3 times don't end in A. Okay, which means we're going to have to figure out how many end in A and how many don't end in A on the previous level, right? Okay, so how would we do that? So I like this idea, but then how do we compute these things? And David, you're saying the next one would be 52? Okay, so what do you guys think here? Last time it ended 6 times, okay. Each gap is 3 to the ith. Okay, that's interesting. Well, I don't, the gap of gaps. Can you say more, David? I'm not sure what you're getting at there. And Sean, your idea was 6 times 2 plus 22 minus 6 times 3. I'm not sure what you're getting at there either. So would you both explain a little bit more? So I got my gaps. I've got a 2, I've got a 5, and 22 minus 18, that's 14? I see the gap of gaps. Here you have 3, here you have 9, right? So that's your gap of gaps. Okay, so David, I see where you're coming from now. So the next gap of gaps would be 27, which means the next gap would be 14 plus 27. Is that right? Because 5 plus 9 is 14. 14 plus 27, that would be 30, 41. Well, that's saying, and then that's what I would add on to 22, right? So that would give me 63 for my next one. But
what I was saying is that we know that we'll have 6 from the length 2 that end in A, and they're the 6 from the right-hand side that we added an A to the end of. We didn't add an A to the ones from the left-hand column, right?
Sure.
So we know there's 6 that end in A, and we know that there's then 22 minus 6 is 16 that don't end in A. The 16 that don't end in A, we can add all 3 letters onto the end. And the 6 that do end in A, we can only add B or C onto the end. And that's how I came up with 6 times 2 plus 22 minus 6 times 3.
Okay, so you're just doing this thing, right?
I'm just doing that thing, yes.
Yeah, okay. And so then here's my question. In general, how do we know how many in the previous level did end in A versus how many didn't? Does that make sense? Like, so, because what we're trying to find is a recurrence relation. What we're shooting for here, maybe I should be more clear, is I want, the number of strings at some level, the number at some level is going to be equal to, the number in a previous level, plus the number in, 2 levels back or something. I'm just making this up. This is just the Fibonacci numbers, which obviously this is not, right? But this is just an example of a recurrence relation, right? Where here I'm saying, okay, well, the way I get 22 is to add up 3 and 8, let's say, right? Which obviously that's not the right answer. But you see what I'm saying, right? Where you're going back. So you have the right idea of going back to a previous level. That's right. But then you're dividing up the stuff in the previous level into these different groups, and that I'm not sure how to count. Does that make sense? Okay, Nathan. So you're saying, what if we, so you noticed it looks like that 8 plus 3 is 11, and we got 22 here, right? Um, so so maybe we take the previous two, um, add them and multiply by 2. Well, does that rule work here? Oh, it does work here. Here we would have 1 plus 3 is 4 times 2 is 8. So here's Nathan's idea, right? Which does seem to work in at least in the first 2 places where we can test it. 1 plus 3 is 4 times 2 is 8. 3 plus 8 is 11 times 2 is 22. Let's see, what would our next one be? Our next one would be 8 plus 22 is 30 times 2. That would give us a 60 right here. Okay, so that's different than what we thought we were going to get from the powers of 2 sort of difference, right?
It is actually the same thing that I came up with going back and multiplying by 2 and 3, like I described, was 60.
Okay, so 60 matches with your answer. So that's a pretty good indication that that's right then, if we got the same thing 2 different ways. Okay, so that's nice. So let's think about this then, right? So if we go back 1 level times 2 and then another level times 2, what's going on there, right? So if we think about this guy, right? We go back 1 level times 2, there's A, B, and C. Well, that could be like sort of, here you're multiplying by 2 as well, right? Oh no, you're multiplying, well, here you're multiplying by 3 in a sense, because you're saying, okay, you have, well, no, I'm not going to go that way. That actually doesn't make sense. Never mind. Okay, so let me ask the question one more time. If this is right, why is it right? Why? So what is this recurrence relation really doing?
So it is actually kind of like multiplying by 3 and multiplying by 2, because the number in level 1 is included in level 2 already. Like the A, B, and C, when we go to level 2, we're discluding the right things. I don't know, maybe
Yeah.
I lost that train of thought, actually. Sorry.
Okay, well, maybe here's a way of looking at it, right? So we have A, B, and C, which is sort of like the first letter here. Here's A, B, and C in the first letter, A, B, and C in the first letter. And that's getting multiplied by 2, right? And then we have this 1, that's getting multiplied by 2 to put in here, right? So maybe 2 times the things that end in A, right? Maybe the things that end in A, right? Those would be, oh, sorry, the things that don't end in A, pardon me, right? For those examples, you could put 3 things at the end. Yeah, I'm not really sure how to go forward here. So sorry, I'm not sure who was speaking a moment ago. Was that Sean? I think I lost track of your argument there. You lost track of it too. Okay. Fair enough. B and C in case 1, it can be seen at the end. Okay. So maybe this A, B, and C, those can be considered the last character, and we can add things onto the front instead. Okay, so we're using Sean's formula. In case 0, where we don't have any characters, that can be seen as the ones that don't end in A. 1 times 3 is 3. Okay. So the ones that don't end in A, that would be the sort of length minus 2 ones. But they were multiplying by 3 instead of 2, right? Okay, and in case 1, B times 3 and C times 3 is 6, and A times 2 equals 2. Right. Well, I mean, I agree with that. I mean, that's how this formula is working. But the issue I'm having here is I don't see how that correlates to this times 2 both ways, right? So maybe let's do, so there's a lot, this is a big mess. Let me do some better writing here, okay? So maybe what we should do is actually write out some of these options, right? Or at least see if we can figure out how to construct them, right? So what we could do is we could say, okay, well, for the strings, so just thinking about this for a minute, let's forget about this for a sec. Let's focus on this one. I think maybe that'll help, right? So if we want to build strings that don't have AA inside, it looks like we're going to be looking at strings that are 1 shorter and doing something to them that doubles the amount we need. And we're looking at strings that are 2 shorter and doing something to those that double how many of them there should be, right? So if we look at strings that are 1 short, right? So let's say we have, A, B, right? 1 shorter. So let's think about 3 for a minute, right? So we could have like an A, B. Interesting. How would we look at that? Well, that's convenient. We're at another hour we have another break, so let's take 5. I'll let you guys think about this a bit, right? And let's see if someone can come back with the actual answer, right? So I'll give you 5 to think about it. Okay, we'll be back soon. All right, was anyone able to figure out what's going on here? So I think the trick is going to be thinking about, instead of the strings, whether or not they end in A, let's think about whether or not they start with A, right? So what we could have on these strings here is we could have a situation where they start with A or not, right? So they start with A or not, right? Okay. So if they do start with A, right, then what do the first 2 characters have to be? A, B, or AC? Okay. And if we're talking about it starting with A for a string of some particular length, and we know that it starts with A, B, or AC, how many different strings of that are there going to be? Right, so if you have a string of length 10, and you know that if it starts with A, it has to start with A, B, or AC. It can't start with AA. That's impossible, right? We have a string of length 10. It could either start with A, B, or AC. What remains to be chosen for that string? Eight more characters, which in terms of our recurrence relation would be how many? We also can't repeat A in those, which is why we're using that recurrence relation, right? So how many would there be? Yeah, the same number as for length 8, right? So we're picking the rest of those 8 strings that and we're saying, well, it can't have AA in the rest of the string, right? When in a string of length 8, well, we know what that is. That's the number of strings that don't have AA of length 2, or sorry, L minus 2, right? And we have 2 different options for what we can start it off with. So we have 2 times that number. Does that make sense? Okay, it does. So what if a string doesn't start with A? Then what would it start with? Either B or C. And in that case, we're going to have 2 different options times the number of strings for the remaining length. But now what's the remaining length? Yeah, 9, the number of strings at L minus 1. See how that worked? Yeah, it's always real clear in retrospect, right? Yeah, you were really close there. You were really on the right track with the ending in A, but you just had to look at starting with A. Maybe you could, and here's something for you guys to think about. Maybe you could adapt this idea for thinking about things whether or not it ends in A instead of whether it starts with A. So I'll let you think about that and see if you can sort of adapt this idea to ending idea rather than starting. Yeah, it's the same thing, but backwards kind of. Yeah, sure. So yeah, I'll let you guys think about that. Well, let me ask you this. Let's try to find a closed form solution, right? So what we actually have here is a linear homogeneous recurrence relation, right? So we have our sequence. Let's call this A, right? A sub L equals 2A sub L minus 1 plus 2A sub L minus 2, right? And we actually know how to solve one of these things. We learned it last term, right? So how would we do that? Does anyone remember how to solve one of these guys? Yep. So we start off with a characteristic equation, right? We've got chi squared minus 2 chi minus 2 equals 0. Okay. And I guess then we would use the quadratic formula to solve that, right? And then we would come out with our roots. But unfortunately, that polynomial doesn't split. So I guess since we have kind of limited time, I guess I was going to move forward and solve the rest of that problem, but this polynomial doesn't split, so it's going to be really gross.
Well, I was actually just thinking about this. The a to the n are going to be like the Fibonacci numbers at n times 2 to the n, and the general equation for like a Fibonacci number of n is really gross, and it has those like square roots of 5 and stuff in it.
Yep, exactly. So yeah, so we're going to have like 2 times that or something. Yeah.
Like 2 to the n times that, I think. Because you put a 2 in on each n.
Right. Agreed. Because each time that you go up another level, you have another factor of 2. So it'd be, yeah, like 2 to the L, right? Yeah, I see what you're getting at. Yeah, definitely. Okay. Yeah, but it will be gross. And you can see that because the polynomial doesn't split. So, but what you could do is you could solve this for chi, go back through, you have your base cases, right? Your base cases are up here. You have, at 0, you have a 1. So, you would have, a sub 0 equals 1, a sub 1 equals 3. So you could use those as your base cases once you solve this guy out and do the linear system, yada, 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 to try to find that result. So what do you guys think? Does that make sense? Okay, so let's try another example, right? All right, so for this one, let move this up here. So we're going to do something a little bit similar. So let a sub n be the number of permutations remember permutations means orderings, right? Orders or orderings, if you want to put it that way, of numbers 1 through n, where no number is moved more than one place from its natural position. Each number is no more than one space away from its original position, I'll say. Okay, so let's do a couple of examples. I'll pop them up here. So can someone give me, let's list out some of these permutations again, right? So if I just have A1, well, that's just going to be 1, right? How about A2? Well, if I just list the numbers, all the possibilities out, right? It'll be, 1, 2, and 2, 1. So how about A3? So let's list out all of them, and then we'll just strike through the ones that that don't follow the rule, right? So what are all the possibilities for A3? Okay, 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 3, 2, 1, 3, 1, 2. Right? And so which of these are going to be excluded? The last 3, right? Because this one, the 1 is moved 2 spots from its original position, so that's not allowed. And in both of these, the 3 is moved 2 spots from its original position. The 3 is moved all the way down to the front, so we wouldn't be able to use those, right? Okay, cool. So now what? Oh, I guess I should tell you what we're trying to do. We're trying to find a recurrence relation for these guys, right? So what do you think we should try next? You can only do switches on adjacent characters, and once they've been switched, you can't switch them again. So there's a length number of 2 switches you could make. Okay, sure. I think that makes sense. How does that help us? Or maybe should we try A4? What do you think we should do next?
So then just thinking about A4 in terms of like switching characters,
Mm-hmm.
you can switch the first 2 characters, you can switch the middle 2 characters, you can switch the last 2 characters, and you can switch the first 2 and the last 2. So there should be 4.
Okay. So you think there's 4? Well, look. So then let's list them out. Let's try A4. Right? You think there should be 4 possibilities? Let's see if we can list them all. Right? So obviously 1, 2, 3, 4 is in there. Right? Okay. What else is in there? 2, 1, 3, 4. Okay. 2, 1, 4, 3. Okay. That's switching both pairs. Okay, what else? 1, 3, 2, 4. Okay. That's switching the middle ones. But there's one more, actually. Oh, sorry. Someone said the middle one, the final one. Nathan said it. 1, 2, 4, 3. We could switch only the last 2. So there's the original. There's one where we switch the last 2. Yeah, 4 switches plus the original one. I see what you're saying. Sure. Okay. So so what have we got here? So numerically, we've got 1, 2, 3, 5. Right. So we've got 1, 2, 3, 4. And here's our numbers. So here's the length. Here's the numbers. 1, 2, 3, 5. Oh, and Nathan, you're guessing Fibonacci numbers, huh? Okay, so that could be. I mean, we could try A5 and see if we can get all 8 of them. But I don't know. Is that what we should do next? Should we try to think about, if it really is Fibonacci numbers, what's the sort of the rule, just like the rule that we found up here where we start with A or not, and we, make up all these, this rule here. Can we think of a reason why Fibonacci numbers would be the recurrence relation here? Or should we do some more examples and check if it's really true? What do you guys think? Okay, you'll check A5 equals 8. Okay, fair enough. What about the rest of you guys? What do you think? Okay, so let me give you guys a hint. Since we're running a little short on time, I wanted to do a couple more of these, so I'll give you a hint here. You start with the numbers in the correct position, right? So correct starting positions. or maybe I'll say switch the first two. How about this? Switch first two or don't. How about that? Right? For those that don't, we have how many different ways of switching around the rest of them. L, the number sub L minus 1. And if we do switch the first two, then we have how many remaining for the switch? Yeah, the number sub L minus 2. Very nice. Good. So you got it once I gave you the hint. Nice. Right? Okay. Any questions about that one? Does that make sense? Okay, let's try another one. I'm out of paper. Okay. So let's try let's try this one. Okay, so there's a row of n seats. Okay. Sn, S sub n, be the number of seatings where no two students are sitting next to each other. So where no one sits next to each other. Where no one is adjacent. How about that? Right? So you're going to take your SAT and you go to the testing center, right? And they space everybody out so that so you can't cheat, right? So you have this row of n seats, but no one's allowed to sit next to each other for cheating. Everyone's all spaced out, right? At least one chair in between everybody, right? So let's see if we can count up a few of these, right? Now, it doesn't say how many students there have to be, right? So we could have 20 seats and only put one person in there if you want. That would satisfy our rule, right? So we have no restriction on how many students, right? How few students you could have, right? There would be a restriction on how many students you could have. If you have 20 seats, the most you can fit is 10 students, right? If you're going every other, right? But you could have less than that. You could have like 4 students and 20 seats or something like that, right? So let's go through the number of seats and figure out how many different arrangements there could be, right? So for one seat, so here's our number, and here's our number at L, or here's S. Should probably stick with the letters I've started using. Here's N, and here's S sub N. Right? So with one seat, how many different arrangements could we have? More than one. Two, right? Why would it be two? Yeah, with or without a student, right? Maybe no one showed up to the test that day, right? So there's just no one there. Okay, so 2 possibilities. Great. Okay, how about 2 seats? Right, so let's start thinking about this. So we have 2 seats. What are our possible? Well, yeah, it'd be 3, because what we can't have is a student in both seats. We can't have that. But the other 3 possibilities are fine, right? So 4 total. There's either both empty, one full, one empty, empty full, or full full, and only full full is excluded. So we got 3 there. Okay, so let's try 3 then. Well, first of all, what would the total be for 3? including the ones where people are adjacent. Not 9, yeah, 8, right? Because each seat can either have a student or not. So there's 2 possibilities here, 2 here and 2 here is 2 cubed total, right? Yeah, nice. Okay. So then what's excluded? Well, all 3 seats full is excluded. So is this one and this one, right? Any of the rest of them are fine, right? Okay, so we would have 5 here, is that right? Looks good. I actually have a different one on here, and I'm a little concerned that we're getting a different answer than I thought we would get. Okay. Okay. So we did something a little bit different than what the problem was asking. There has to be at least one student. So I screwed that up. So the arrangements here, I knew something was going wrong. So we would have only one arrangement here. If we have to have at least one student, here we would still have 3, I think, or 2 in this case. Yeah, now just 2, because we would just have here or here. They could be in either one or the other, but there has to be a student there and it can't be both. So that would be 2. Okay, so what would we have for 3 then? 4? Yeah, I think that's right. So what would the 4 of them be? So let's set it out here. So 1, 2, 3, 4. The same 5 minus the empty. Okay, so the ones we do have, we could have a student here, 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 or both. Right, so that would be the 4. Yeah, exactly. Yep. Okay, so let's do one more row. Since we screwed that up, let's all get on the same page. So what's the next one going to look like? 4 seats. So we've got, a student only in seat 1, 2, 3, or 4, right? So we've got x dot 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 x dot 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 x dot and dot 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 x. Okay, so we've got those 4. We could also put in 2 students. We could put them in here and here, right? Or we could put them in here and here. Or we could put them in here and here. Can we put in 3 students into 4 seats? No, right? Okay. So here we would get 7 then, right? Okay. So I think I got them all. Here's all the ones with 1 student in 4 seats. Here's the ones with 2 students in 4 seats. I think I got them all. Did I miss any? I think we're good there, right? So what do you guys think? Anyone see a pattern? Okay, so we could do 1 plus 2 plus 3. That could be. Maybe we should we do one more on here? Or can you think of a reason why it would be the previous 3 added together?
So I think the reason it has to include not just the last two terms in the sequence
Mhm.
is because if you think about it in terms of like the starting string, right? It can be X, or if you have like two characters at the beginning, they can either be OO, XO, or OX, right? But like if you have an X at the end, you can't add another X at the end, so you have to look back extra.
Okay, so I like your idea of looking at, the whole idea of a recurrence relation is you start with the old stuff and you add something new. You add one more thing onto it and see what happens, right? So I like your idea there, but let's go through that carefully. Now, do we want to add a new person at the front of the row, or should we add a new person at the end of the row? Or, pardon me, not a person, a seat. Should we add a new seat at the front or at the back? The back. Okay, sure. So in that case, what we're going to have is we're going to have two situations. The seat at the back is empty. Back seat is either empty or filled. Okay. So if the back seat is filled, right, then, sorry, let's do empty first. If the back seat is empty, what about the previous, let's see, we have, now we have, N seats. The back seat is empty, right? So the previous string could end in a student or an empty seat, doesn't matter, right? So here, how many seats are we trying to fill? Well, n minus one, right? And how many of our s sub n minus one would we be able to use if the back seat is empty? Any of them, right? Cool. So that would be s sub n minus one. Okay, what if the back seat is filled? Then what would we need to do? So we have a bunch of seats, right? The back one is filled, right? Then this one has to be empty, which means these ones are the ones remaining that we get to mess with, which would be s sub n minus 2. That's almost right. What else might happen besides just doing all the arrangements of these which have students in them? See what we missed? Yeah, we could also have all of them be empty because now we have another student in there again, right? So remember, we have to have a student in there somewhere. That was our original mistake. But now that we put this student at the end, there's this extra arrangement where all these seats are empty. So it'd be s sub n minus 2 plus 1. And now I think you can probably see it, right? Because now if we have, s sub n, let's put it down here, s sub n equals s sub n minus 1 plus s sub n minus 2 quantity plus 1, right? Well, 1 plus 2 plus 1 is 4. 2 plus 4 plus 1 is 7. And what we should get for the next one is 4 plus 7 plus 1 would be 12. And I'll leave that as an exercise for you guys. You can check and see if you can find the 12 arrangements for 5 students, right? Everyone happy with that? Any questions there? If we hadn't excluded the empty set, it would just be Fibonacci. Yeah, that sounds right. Yeah, I think that's right. And our base cases would be different as well. So it would be a different recursive formula and different base cases both. But yeah, I think that's right. Cool. Yeah, it starts with 2, 3. Yeah, I think that's right. Because we wouldn't have that extra +1 on there. All right, cool. So we have not very much time at all to talk about your lab, but that's okay. We're going to do our best, right? Cool. So let's jump over here. Oh, and I think I need to download it. Uh-oh. Give me one moment here. So we want lab 4. Lab 4, there we are. And today we're going to be talking about a 3-dimensional cellular automata. So if you took me last term, then you'll remember that we did, oh no, that's the one that we skipped actually. Oh, okay. So this will be interesting. That was lab 3 that we skipped last term. Okay. So a cellular automata, the idea is that you derive it's a recurrence relation, so it's much like what we were doing just a moment ago, but you derive the position of cells or the presence of cells based upon the position of the presence of other cells. So for example, it's like Conway's Game of Life. Did we do that last? No, that was in CS 161, I think. Right? So for example, if you have a rule like, you know, anytime, yeah, you may have looked at it, but that lab got screwed up for some reason that week. So you probably just looked at it, but most people didn't. So what's happening is you have this arrangement of cells that can either be on or off. And since the cells can be on or off, I'll just represent them in binary. So I'll say I have 0, 1, 1, 0, 1, 0, 1, 1, 1, 0, 0, 0. Okay. So there's an arrangement of cells that are on and off. And what you do in a two-dimensional cellular automata is you derive a new row from the old row. And the way that you do that is a set of rules. Here's your set of rules. You look at the arrangement of 3 cells above you. How many different arrangements could there be of 3 cells? If the contents of each cell is binary. Yeah, 8 of them, right? So what you do is you have these 8 different rules. 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0. And each of these has either a 0 or a 1 attached to it. So let's, I'll just make this up. 0, 1, 1, 0, 0, 0, 1, 1. And this is a rule. Okay, now what you do is in building the next row, you look for each one of these patterns, consult the rule, and find which new cell to put in. So for 0, 1, 1, we have a 0 that's supposed to go there. Next, we have 1, 1, 0, which is supposed to be a 1. 101 is a 1. 0, 1, 0, what should we get for the next one? 0, 1, 0, that should go right here, right? So what should I put for my next entry here? 0, 1, 0 lives on top of it. So what does it generate? 0, good. This one, 0, 1, 0 gives us a 0 out. Okay, let's do the rest of them. 0, 1, 1. Oh, sorry, 101 is the next one. So what's 101? 1, good. 101 gives us a 1. 0, 1, 1, that'll give us a 0. 1, 1, 1, what'll that give us? 1, good. 1, 1, 0, that gives us a, oh, sorry, 1, 1, 1 gives us a 0. Sorry, my bad. 1, 1, 1 gives us a 0. 1, 1, 0, that gives us a 1. 1, 0, 0, that's a 0. 0, 0, 0, that gives us a 1. And usually what we do is we wrap around the edges to sort of, so, because otherwise, you know, if we're here, we're just like missing something on the other side because we have 0, 0, you know, missing. Usually what we do is we just wrap around, you know, these guys to the other side from each other. So we would have 0, 0, 0 here, which is a 1, and 0, 0, 1 here, which would also be a 1. Perfect. And that's our next row. That's a two-dimensional cellular automata because you keep expanding this thing downward. You do the same thing again on the next row and then on the next row, and you get this sort of black and white image with pixels on and off, right? You could think, you know, if you drew this with black and white squares for the zeros and ones, you get a black and white image. Now, what you're going to be doing is that same idea, except in 3 dimensions. And you're going to start out with an arrangement of cubes like this, which are either on or off. So you'd have 0, 1, 1, 0, 1, 1, 0, 0, 0, 0, 1. Okay. So you have these cubes. So there would be a cube here, right? So there's this little cube, you know, sitting here, right? There's a cube sitting here, right? Those would be the ones, have a cube sitting there, because now we're in 3D, right? And the zeros don't have a cube sitting there. What you do is you take this slice, right? This horizontal slice, and based on the presence or absence of cubes underneath you, you build up more cubes on top. So the whole thing goes, this time I just made it go upward instead of downward, but it's the same idea. You're taking slices and then going up. Here you're taking slices and going down, but it's the same idea, right? And you're building up these new layers of cubes on top of the old ones, right? So let me ask you a question. How many different slots do we need for the rule now if we're in 3D? And so if we have this situation here, right, where there could be, you know, we're wondering, you know, this whole thing is a little layer, right? Right? And there may or may not be a cube in this layer. And what we're wondering is, what do we put on the next layer up, right? Do we put a cube in this center square here? Do we put a cube on top of this guy or not, right? So there'll be more than 16 because there's 9 different locations that we're going to be looking at. Here we were looking at 3 locations, right? And saying, you know, oh, well, from these 3 locations on top of my 0 right here, you know, do I put in a new one or not? Here I've got 9 locations. So how long does my rule have to be? So my rule is going to be 2 to the 9th bits long, right? Because I could either have a square here or not, or pardon me, a cube here or not, a cube here or not, a cube here or not. So you have all these different possibilities for the layer underneath you to determine whether or not you're going to put a cube on top, right? So it'd be 2 to the 9th, which is 512, that's right. 512 different possible rules you could have, right? Is everybody good with that? So let's take a look at the code real quick. Sorry, I'm going to go a little bit over today to try to get you set up for this lab. I'm sorry about that. Give me about 5 minutes and I think we'll be good. All right. So, oh, and just let me turn my, okay, I did turn the video off. Okay. Okay. So coming down here, we still have our resolution, same as before. That's how many cubes we're dividing up our space into. There's a little refresh right here because it's actually going to draw for us in real time, which is fun. I've got my array of cubes, which is res by res by res, which is Booleans, right? How many cubes are in there? And my rule, which has 512 different bits inside of it, right? So here's my lighting, that's the same, normal's the same, draw a cube, that's the same as before, right? Built of drawing triangles. My draw object here, that'll be new. Main, display, check, okay, all these guys are the same. And rule is new. So there's build array, rule, and draw object here. So let's go through those real quick. Okay, draw object here. It animates it in the J direction, which is the vertical direction, like Y, right? IJK is like X, Y, Z. So we're animating in the Y direction, meaning we're building from the bottom upward. Right? We start out with a minimum Y value and go up to the maximum Y value. So as I said before in the video, we're sort of building up layers. And what I do is check my array at each location to see if that Boolean array does in fact have a cube there. Right? There's my array of bools called cubes. If there is a cube there, it'll draw one, right? Draw a cube if it's there. If not, it won't. Right? So we just go through every single possible place there could be a cube, check the array, and draw the cubes according to the array contents. So really what we're going to be doing is building up the contents of this array according to the rule. Here's how that works. Okay. There's my rule. Okay, here's build array. Sweet. So the initial cubes array, I just randomly turn on a fifth of them. Okay. So on the very bottom level, right, J equals 0, that's my Y value. So there I just turn on some cubes randomly. Okay. And this clears out the rest of the cube array for the upper layers. Right. So I make sure that the whole array is zeroed out except for the bottom layer. Then I initialize a random rule where 9% of the patterns generate a block on top. It's just random, looking at 9. I create my rule randomly. You can build your rule by hand if you want, but I just built mine randomly. Then you build layers on top of the first, which is you say, okay, for my next layer, right? I guess for all of the remaining layers, I look and see what my rule is according to my location and which cubes are underneath me. And if the rule is true, then I put that into my cubes, right? So what's the rule? Let's look what that's doing, right? So I look at my pattern. You can look on Wolfram Alpha if you want to see a little example of how this is working here. And what am I doing? Well, I'm looking at my pattern number and I'm adding on a power of 2 times whether or not my cube is there. That's binary. Remember, that's Boolean. So either a 1 or a 0. And here I'm just putting in all the different locations where my cube could be underneath me. Notice underneath me, they're all J-1s here. They're all J-1s, the cubes in the layer below. I'm looking at those and saying, okay, well, do I go left and up? Do I go left? Do I go left and right? Sorry, left and down. So we just sort of look around underneath us and use the presence or absence of those cubes to build this binary number called pattern number, right? And then what I do is once I build it, I look in the rule for that particular pattern number to see what cube is supposed to go on top, right? Let's run it, see what happens, and then I'll let you guys go. Please, if you do have questions, please throw them in the chat so I can answer them quickly before we go here. All right, so here's some different examples. And sometimes they build diagonal things, right? Sometimes they just kind of stop. And there's another diagonal one. Sometimes they're pretty full looking. That's a pretty full one. There's another diagonal one. That one stopped. So they appear to be each time it animates, it's choosing a different rule, right? So those 512 different bits, it's filling those up randomly, right? How many different rules there are? Well, that would be 2 to the 512. Lots of different rules, right? But you can kind of see here. Here, let me zoom in a little bit. Spin it this way. There we go. Okay, so that's a sort of a flat one with some skyscrapers. And so many different rules you can have. You would imagine there's quite a few different things that could happen in here. But I'm just randomly generating rules because I didn't want to sit there and list out 512 ones and zeros. But there are lots of things that could happen. It's just randomly when you're picking, it seems to fall into most of these rules seem to fall into a few categories, right? So a fun thing to do would be see if you can make a rule that generates a block of cubes that doesn't fall into one of these categories. See if you can do something a little bit more interesting with your rule. I think could be fun, right? Does anyone have any questions there? And of course, as usual, just turn in a screenshot of the object that you made, right, along with your code. Does anyone have any questions? Just gonna pick a rule. You can change the initial arrangement on the bottom. You can change how the way the rule works. You can change the resolution. Yeah, any of those things. You can pick a random rule if you think you can figure out a way to make the rule do something interesting. You can make it partially random, but I think basically what I want is for you to make a cool shape. So if you think that this shape is cool right here, okay, fine. But but I think it would be more instructive to try to make a shape that's interesting, that doesn't fall into one of these obvious categories. Does that make sense? That one's kind of cool. Okay, sounds good. All right, well, have a great day, everybody, and I will see you next week. See you later, guys.